VLSos here. This is a video lesson on integration by parts. Integration by parts is a integration pattern that can help us integrate challenging or difficult integrals. It's much like U substitution, but it's a little more sophisticated, a little more complicated, and it doesn't always work. But when it works, it can be a very helpful tool. I'm going to come straight out and show the integration by parts theorem. If we can choose pieces for u and dv to structure an integral in terms of u and dv, then we can convert the u and the dv into an equivalent expression, u times v minus the integral of v with respect to u. This is what we call integration by parts. It's like U substitution, but we're choosing two expressions, two substitutions. One is u, and then we would take the derivative of u to establish the du that's needed. And the other starts as a substitution that's a derivative. And we would need to integrate in order to find the v piece. That is a part of what this is equivalent to. Difficult to say, easier to see. Let's say that we had the integral x times the sine of x with respect to x. We might look at an integral table. A short integral table might have how to convert this right away. We could use U substitution and discover quite quickly that that wouldn't help. Integration by parts is what's going to help us here. And it begins by assigning u to be equal to a piece of the integrand. And if we guess wrong, then it won't work, or it'll become something that's more complicated and therefore not useful. And we would then abandon integration by parts, or we would choose u to be equal to another piece to then see if this would work. If we have u is equal to x, then will restructure this integral, but I'll still have the sine x dx left over. There's a second substitution to be made, and it's going to be expressed as a derivative, dv over dx. That will be the sine x piece. And then if we solve for dv by multiplying both sides by dx, that's how we get the sine x dx. That will then be replaced with just the dv. So if I restructured the integral now, I have the pieces that I need to make the integral in terms of u with respect to v. But I need to then convert it to this pattern. And this pattern has u, v, and du as its pieces. I have u, I need v. I'm going to get the v expression by taking the antiderivative of the derivative that I have assigned it to. In other words, if I integrate both sides of this equation, then on the left I get v, and on the right the integral or antiderivative of sine x is negative cosine x. I now have the u and v piece. I still need the du piece. In order to get the derivative of u, I take the derivative of u with respect to x, which in this case is 1, and then solve for du by multiplying both sides by dx. I now have all the pieces to convert the integral into this pattern. And it will be u times v minus the integral of v, or in this case, negative cosine x. I will put the negative out front, turning this to an addition. And then finally du, which is simply dx. After applying the integration by parts step, and getting the new expression, notice of course that the expression still has an integral in it. So I need to continue by integrating. If an integral that was previously difficult creates a new integral that is now possible or easier to integrate, then integration by parts has helped. But it doesn't always work that the new integral is easy to integrate or even possible. So we may abandon it sometimes at this step when we see if it has helped or not. In this case, the integral of cosine x is easy to find. So I'm going to proceed with the last step. I still have the negative x cosine x. The antiderivative of cosine is sine and positive. And then, of course, because I integrated, plus a constant of integration. What was previously impossible, we were now able to do with this integration pattern. Let's show another example. What is the integral of x squared times the cosine of x with respect to x? Let's assume that we may have tried other techniques that might have been a little easier, and we've decided to use integration by parts because what we tried so far hasn't worked. The u substitution that I'm going to try first is u is equal to x squared. And it's good habit to then take the derivative with respect to x right away and solve for the du. We'll probably need those pieces, and it's easy to do once you've assigned u, so it's a good habit to be in. The remaining part of the integral is the cosine x dx. That's the second substitution. dv over dx. The derivative I'm going to assign to be, the derivative of v I'm going to assign to be cosine x. And I'm in the habit of immediately solving for dv and integrating in order to get v. The integral of 1 dv is v, and the integral of cosine x with respect to x is sine x. Now I have my pieces, I can assemble what this integral is equivalent to. It's equivalent to u, or x squared, times v, or sine x, minus a new integral, but of v, sine x, du. And du is equal to 2 times x times dx. The 2 is a constant, so I can put it in front and multiply later. The x is part of the integrand, I'm going to put it in front of sine. And the dx helps me finish the notation for the integral. So I've created a new integral with integration by parts. I'm going to take a look at that integral and think, is it simpler or has it been made possible by integration by parts? It is only a little bit simpler, but I might be challenged in integrating that. The new integral, x times sine x, was done in the previous problem. But in the previous problem, we used integration by parts to get its antiderivative, which means that if I have used integration by parts and I have an integral that needs integration by parts to continue, then I'm using integration by parts inside of integration by parts. That's fine. In fact, it's a common thing to do. Integration by parts can be used over and over and over again until finally you get an integral that, hopefully you do, that then has a relatively simple antiderivative and you can finish. Sometimes integration by parts will create an integral that you would use another technique in order to integrate. Or it may not be possible to integrate and you'd have to stop and use a different technique. In this case, I have to be sure to keep my work well organized. So I have the x squared sine x minus 2, and then I'm going to make big parentheses because the integral of x sine x is sophisticated enough, I've got to be careful to distribute this -2 at the end correctly. So I have inside the parentheses the antiderivative that I've already found, and the constant of integration can go outside. We only need one constant of integration in a problem. And in the last step, I'm going to be careful to distribute this -2. So my final answer is x squared sine x. This -2 times this negative term turns it positive, 2x cosine x. And then a -2 times a positive sine x is a -2 sine x. And then don't forget c. That was integration of parts inside of integration parts.